Today we're going to learn about the Michael reaction, and this is a new way to form carbon-carbon bonds and to add to your repertoire here. So this is another way of forming a carbon-carbon bond using an enolate, and the electrophile in this case is an alpha-beta unsaturated carbonyl compound. A couple chapters ago we learned about conjugate addition, you might remember, where a nucleophile could attack, if it's a specific nucleophile, it could attack the beta carbon of an alpha-beta unsaturated aldehyde or ketone or ester compound. And you will recall that because of resonance, remember the carbonyl is always a electrophile. It's got a partial positive charge on the carbonyl carbon because of the resonance there. But if we have a double bond between the alpha and beta carbon, then we can also, there's an additional resonance structure where that double bond completes the octet of the carbonyl carbon, leaving a positive charge on the beta carbon. And so when you are looking at an alpha-beta unsaturated carbonyl compound, you're thinking there's a partial negative charge on oxygen, a partial positive charge on the carbonyl carbon, a partial negative charge on the alpha carbon, and a partial positive charge on the beta carbon. So some nucleophile can come in and add in that position, in the beta position, and that is what we called conjugate addition. So the product of that conjugate addition, or the initial product of that conjugate addition, if we draw all these hydrogens in here, is that the nucleophile has formed a new bond to the beta carbon here. And if it adds there, then this double bond flips in between the carbonyl carbon and the alpha carbon, and then that dumps the electrons onto oxygen. So we have this conjugated system of four atoms in a row that are in conjugation, and that transports that partial positive charge down to the beta carbon there. So if we follow our arrows here, then our initial product is this with the negative charge on oxygen. Then depending on the source of the proton, and so this looks like an enolate, or if it was protonated there would be an enol, and that would be the unstable form. The ketone or the keto form is the more stable form. So what we end up with as a final product then would be this lone pair dumping back in here, dumping the electrons onto the alpha carbon, and then picking up a proton in some way, some acid source, some acidic hydrogen there, and then the net result would be we've reformed the carbonyl here, and we have now added a proton onto the alpha carbon here that wasn't there before, and then we have added this nucleophile onto the beta carbon that wasn't there before. So it looks like the net result is that the nucleophile and the hydrogen have added to the double bond, and nothing happened to the carbonyl at all. Remember, though, that a double bond normally does not act as an electrophile. It acts as a nucleophile in electrophilic addition reactions. So the fact that the carbonyl is there is the thing that makes it originally have this partial positive charge, and then making it act as an electrophile in order for this reaction to happen. Okay, so that was review. That was conjugate addition. And what we learned a couple chapters back is that you can add a cuprate, a carbon nucleophile that way, and an amine, either primary or secondary amine in that way. So if we use a different nucleophile, if we use an enolate as a nucleophile, then we have a Michael reaction. So a Michael reaction is a conjugate addition, like we just looked at, where the nucleophile is an enolate of a 1,3-dicarbonyl compound. So we could start out with, it's a 1,3-dicarbonyl compound, otherwise known as a beta dicarbonyl compound, has two carbonyls that are separated by carbon. Okay, so you could start out with a beta ketoester, an ester with alpha beta ketone on the beta position. You could start out with a beta diester or beta diketone, and there's lots of other compounds that you could start with. And let me refer you to table 23-1 in your textbook on page 772. And that will list a bunch of different kinds of Michael donors and Michael acceptors. So this thing right here that we're starting out with, the 1,3-dicarbonyl compound, is referred to as a Michael donor in this Michael reaction. And then this is the Michael acceptor. Okay, so let's work through a mechanism here. So if we start out with a sodium ethoxide as a base, then we have very acidic hydrogens here on our Michael donor, so that ethoxide will deprotonate, forming the enolate. And that enolate then is a good nucleophile. One hydrogen left. And then that nucleophile can add then to our Michael acceptor. Coming in, adding to the beta carbon, and so alpha, beta, and so if we add there, we can flip the electrons up onto oxygen there, and our intermediate that we would have, we've now formed a bond between the enolate carbon and the beta carbon of our acceptor compound. And I have not followed my arrows very well. I've already drawn the final product. Okay, so I'm going to turn this into a single bond right here for our intermediate with a negative charge there, and then we flip the arrow, or we flip the bond, the pi bond there. So in this reaction, we have our base has pulled off a proton there, and so now we have ethanol in solution that we have made. ETOH, and that is, not to be confused, don't make it look like that's attached to that methyl group there. Then if we flip back down, the electrons reforming the carbonyl, dumping the electrons onto the alpha carbon, then that can pick up a proton from ethanol, reforming the ethoxide that we started from. Okay, so then our final product will be what I already drew and kind of scribbled out there. And the final product always has this relationship. It is a 1, 2, 3, 4, we can go either direction here, 5. This is a 1,5-dicarbonyl compound. Mycloreactions are always going to form a 1,5-dicarbonyl compound. And if we happen to be using this, what is this thing called? Acetoacetic ester. Remember what we used acetoacetic ester for before? We used it as a way of adding an acetone unit onto something else, and we dumped in H3O, turned this into a carboxylic acid, and then decarboxylated and formed CO2 gas. So if we're using acetoacetic ester, then we can, in a last step here, then add H3O and heat and form our final product, which I will draw kind of in the same way here so you can clearly see what's what. And here is the let's number here first. 1, 2, 3, 4, 5. This is our 1,5-dicarbonyl compound that we made, and here is our original alpha carbon, and this is our original beta carbon. So the new carbon-carbon bond that we made is right here. Carbon-carbon bond. So mycloreactions form 1,5-dicarbonyl compounds, and they do that by a conjugate addition of an enolate from a 1,3-dicarbonyl compound reacting with an alpha-beta unsaturated carbonyl compound of some sort. So this is just one example, and the next video will work through a couple more examples so to get you more comfortable.